So, our last but not least speaker for today is the man himself, Massimo, who will talk about, I think he's a candidate for the longest title award or something. Some reflections on the use of structural equation modeling for investigating the causal relationships that affect search engine results. I need something to drink now. So, Massimo, thank you. Stage is yours.
Sure. The title is long, but the talk will be. I imagine that we could run in late, so I prepared only a few slides. Indeed, for this presentation, instead of some reflections, I should say a very few reflections, and for the others reflections, please go to the paper. So some years ago, I was attracted by the problem of bias and unfairness in IR, and in general, in many other information systems dealing with users searching for or asking for recommendations. And I realized that structural being a useful framework to address the problem for a series of reasons that I will try to explain. So my name is Massimo Melucci. I am from the University of Padua, and I've been working in IR for quite a long time. So let me introduce a few motivations and the general approach that I described in the paper. So the main, the initial observation was that the way information retrieval systems, but the same can be said about recommendation systems and other systems, in a very obscure way. I mean, we don't know how a system decides what to retrieve, how the item is placed in a ranked list. So these systems are often a black box. The internal mechanisms are often hidden to the end user, especially sometimes also to the researchers. In IR specifically, we don't know how documents are gathered from, for example, for the World Wide Web, how the documents are indexed and how the content is represented, how the documents are selected and then ranked. It is true that we have some documentation, some papers describing, but as the researchers in reproducibility can confirm, these details are very often missed. Another reason why we would like to have some information about how the systems work is that these systems fail to retrieve relevant documents for some topics. For example, we have difficult queries. Many systems cannot retrieve an acceptable number of relevant documents, and the reasons we fail is even unknown. And if we could have a way to know why our system, for example, cannot retrieve relevant documents enough, we may improve our system but that requires a sort of microanalysis that is very difficult to carry on during our experiments, where we are used to run to run the system many times with different parameters, and then compute average measures to have a general idea. But we don't know how and why the system behaves for a specific topic, and why some frameworks to understand the internal mechanism of a system is bias and fairness. So today, Carlos explained us how bias affect search and why and how the system should be fair. So the understanding of whether a system is fair or not again requires some methodological framework to address the problem. The good news is that these situations occur often in other disciplines like economics, social science, psychology, and many others. Today also Nick mentioned the computational social science as an example of how different disciplines can interact together with the same goal. So we are in a similar situation in the sense that economics, social science, etc., can suggest to the researchers in information retrieval some tools to investigate how the systems work. And these situations are often addressed by structural equation modeling. So in the paper, I described what are the pros and cons of structural equation modeling. And I try in this short talk to explain what is SEM and how it can be used to address the problems I mentioned before. So let me very quickly repeat something that everybody should know, at least in this workshop. So in general, a retrieval system collects some data, for example, from the World Wide Web. The pages are then indexed, the content is represented in somehow. All the data are stored in an index from which the system can retrieve possibly relevant documents to answer the user's requirements. So what's important here is that at every step of this complex process, there are sources that affect somehow the decision made by the system. So some factors affect what to gather from the World Wide Web. Some other factors affect the way the content is indexed and represented. For example, the information retrieval designer can decide what to index, how to select the words, how to represent the images, etc. And similarly, the algorithms that select the data to meet the user requirements are affected somehow by the context. So today it was mentioned Ricardo Baeza Yates and a nice picture where all the sources of bias are summarized in a very nice way. So I would like to refer to that picture to have a better idea than I can did with this one. But basically, the problem is that the system and the designers thereof are not neutral. So something has said happen in other disciplines. In these disciplines, we have often we can often see that a structural equation model is used. So, what is a structural equation model? So for those who know statistics, such a model remains somehow a regression model. The basic difference is that there's a clear distinction between latent latent variables and observed variables. So X and Y are observed or manifest variables, and Xi, eta, delta, and other Greek Greek variables are latent variables. So in these models, there's always some latent variable that cause the production of manifest variables. So this is the meaning of the arrow, for example, from Xi to X. There's also an arrow between from Xi and eta, meaning that Xi is latent and exogenous, so a sort of independent variable, whereas eta is latent but endogenous. I mean, a variable that is affected by other. So we have two kind of relation. One relation is from the latent to the manifest variables, and the other between variables. So the manifest variables are not directly connected through, for example, correlation, but the correlation between the manifest variables are caused by the latent variables. This graph can be mathematically represented. Sorry for the math, but we cannot avoid. But let me only to point out two aspects. Only X and Y are observed. Anything else will be estimated. In particular, the matrices lambda, B, gamma will be the parameters to be estimated. These parameters are basically regression coefficients. What the designer has to do is to decide how many latent variables to have and how these latent variables are connected each other. Once these choices are made, and starting from the observed data, a software can, in an automatic way, estimate all the regression coefficients. The coefficients, the latent and the manifest variables, and the coefficients between the latent variables. Basically, these coefficients are a sort of weights of the graph of variables just showed before. So how we can use SEM? We can use SEM by defining a structural equation model to describe the data observed at the different level, at the different steps of an information retrieval process. So we can observe the data, for example, of retrieved pages given as answers to some queries. And these data are then collected and the model can be estimated. This model can be used to interpret what's happening, how the system is performing. The same can be done if we want to observe how a system represents content, how the system retrieve and rank documents, and etc., etc. Okay, an example explained in the cited paper. For space-time reasons, I cannot, of course, explain everything into the detail. But in this example, we have a structural equation model trying to explain how a retrieval system ranks the document given from a large web page collection. The data were taken from the Microsoft Learning to Rank dataset. Using these data, it was possible to estimate the following model, where we have 5 latent variables. Each latent variable, like content, generates the observed data, and these data are extracted from the dataset, the Microsoft dataset. For example, content is a latent with every to the pages. Graph is a latent variable regarding everything what is related to how the web pages are linked together. So, for example, it can be used to measure how the system uses authority measures to rank the document. The same link is a latent variable regarding everything about anchors, URLs, etc., etc. We have also latent variables describing the quality of pages, and also a latent variable describing how the user is interacting. I mean, how the system is exploiting the data about the user behavior to rank the documents retrieved as answer to the query. So such a model, when it made and variable we have a coefficient, can tell to the experimenter how the system works. So starting from a plain ranked list, ranked document list, we have such a model. So let me conclude with a few reflections. SEM starts from correlations. So the only data given as input to estimate such a model is a sort of correlation matrix between the manifest variables. These models aim to find some, let's say, cause relationships between the variables. For example, graph information are used to rank the document. However, correlation does not imply causation. So, for example, we may have a latent variable called in general growth that has a positive impact on age and also on weight, but we cannot conclude that height and weight, which are manifest variables, are correlated. They are correlated only because they share a common latent variable. So what we observe from height, about height and weight, can be used to infer whether there could be a latent variable that is called, in general, growth. One weakness of structural equation model can fit the data, but unfortunately, it might not be the only one. So there might be other models that explain the same data. And in a similar way, the observed data can help estimate a given model, but if the sample of data is changed, we might estimate another model. So there is no, unfortunately, a one-to-one relationship between what we observe and the structural equation model that we want to fit. By the way, this is common in statistics, but so it's not a weakness only of structural equation model. So, however, SEM is probably the most general framework used in social statistics, economics, and many other fields to explain why and how a system works in a given way. So SEM, from this point of view, is a promising framework because it is quite flexible in the sense that we can decide how many latent variables, how many manifest variables to add to the model, and then fit the right model. So even though it is imperfect, it is often preferable to not have any model. So because perfect is, as you know. So SEM is a good starting to address the problem of interpretability, explainability, and especially in information retrieval. So I finished. Thank you very much for your attention, and thank you, of course, for participating to the workshop until now.
Okay, thank you very much, Massimo. Are there any questions or comments? Might be more comments, maybe, because it's about reflections.
We are so tired.
I have some comments, if nobody else wants to start. So your example, when I saw this, it reminded me a bit of some work from the 90s, from Ulrich Thiel, who I worked with later then, because he created an interactive IR system using abductive logics, so abductive retrieval. And as I said, it's just a comment, but it reminds me a bit of that, because the idea also was to explain to not only interaction, but also to improve explainability of results. So they had this system. I think it was an arts database or something, and when you typed in a year as a query, like I don't know, 1975 or so, then the system would have rules saying, okay, that a year of birth is a year, or a year when an artifact was created is a year, and of course it would then apply abduction, so the other way around. Observe that you type in a year, and then it would ask, what do you mean? Year of birth, year of some art was created or whatever. So this is this somehow related to what you are saying? I mean, it's not about latent variables so much because
it is related because Tia's work, but also my work, Ricardo's work, belong to the general category of explanation. So the explanation of information retrieval systems, or in general of information systems, dates back to probably many decades ago. So, for example, in health system, where one of the first systems subject to explainability studies, you know, probably the field of expert systems in medicine, supporting the doctors for diagnosis, etc., etc. So many techniques like logic stem from that area. Deductive logic and other logics are powerful tools, but they lack of generalization. So you have to build the model, you have to ask experts, etc. And that implies some sort of knowledge that cannot be always available. So purely statistical techniques like structural equation modeling, but also other frameworks similar to SEM, do not make any assumption, do not require any knowledge or encoding into deduction, induction, implication, whatsoever. So the answer to your question is that they are related because they address a similar problem, the same problem of explanation, but the approach is very different because SEM derives from the community of statistics, logic from mathematics.
So in a way, the logic-based or abductive.
It's just religion.
So in a way, the abductive approach would be more the information science solution because it comes from the user in the end with rules, and this is the statistic that would be the data science variant. Is that correct or?
Correct. Yes. Yes.
Okay. Okay. Any other comments, questions?
Just a comment. It was nice how you linked your talk to all the not all, but a lot of the previous talks today. So it was a nice way of finishing the day.
Thank you for your question, because when I started discussing with Ingo and Haining about this workshop, I was working on this topic, in the sense that I think that data science and these frameworks like SEM that can be put within data science, at least from the point of view of statistics, can be seen as an example or an expertise, a special expertise can be used in fields like information retrieval. Indeed, the paper that is cited in the slide was authored together with a colleague of mine who is a statistician, expert in social and economics and economic statistics. So I believe that this kind of frameworks can be useful. It's not much different from what we already do when we use statistics in IR, for computing, for example, p-values or for estimating probabilities, etc. Here, the idea is to try to enlarge the horizon, try to speak to other experts, like Nick Belkin suggested, and not only to confine ourselves to reading one textbook in statistics and reuse formulas without understanding anything behind. But collaborating with other experts is crucial. For example, I submitted the first draft of the paper to Alessandro Alpaggiaro, who made a lot of comments and corrected the dozens of errors I made in the first version. That means that we always should be humble, and if we wanted to do really something interdisciplinary, we have to accept to cooperate with others and to use their expertise. So this paper and this talk is related to the workshop in this way. There's a personal experience on this subject, on this topic.